Howdy. We got a request to consider problem number 15 in your reading. In problem number 15, we have a function f of x equals x e to the x. And we're asked to show that it converges for all x. Sorry, that its Maclaurin series converges for all x to this function using the remainder. And so the difficulty that we had is turning this error bound into an argument. Like so. Here our center, because we're dealing with the Maclaurin series, is our center is 0. And so the issue that we have is figuring out an expression for this guy, because what we want to show is that as n goes to infinity, then Rn goes to 0. And so the question is how to make that happen. Well, for this we need an expression for the n plus 1th derivative. So the only option that we really have is to start taking derivatives and look for a pattern. And so when I take a first derivative, I get, using the product rule, t e to the t plus e to the t. When I take the second derivative, I get, from this term, I get t e to the t plus e to the t, plus from this term I get another e to the t. To me like a pattern fairly quickly emerges, and I can verify that with yet another derivative here, t e to the t plus e to the t, plus our original 2 e to the t's there, gives me t e to the t plus 3 e to the t. So how would we describe our pattern? Well, our pattern looks like that when I take the nth derivative, what I get is t e to the t plus n terms of e to the t. So, two things. One is, can I prove this pattern? A practical mathematician at this point might just say, I've got a pattern, it's pretty obviously correct, I'm just going to use that. And in fact, that's exactly what we're going to do, is to simply assert that this pattern is correct and use it. But let me take a little side note to prove that this pattern is in fact the case, so that I can remind you of proof by induction. Remember that with a proof by induction, we start off with a base case. In this case, we're going to start with our base case at n equals 1. And we've already done that. In our pattern finding, we found that the first derivative was equal to t e to the t plus 1 times e to the t. And so that establishes that our proposition is true for n equals 1. Then for the induction step, we show that if our proposition is true for n, it implies that our proposition must be true for n plus 1 also. So we will begin by assuming that the nth derivative is exactly what we say it is. Namely, it is t e to the t plus n times e to the t, and therefore our n plus 1th derivative is the derivative of that. And we use the same pattern that we did in finding our examples. First times the derivative of the second times the derivative of the first, and of course plus n factors of e to the t. And lo and behold, we have n plus 1 factors of e to the t. So that if my nth derivative is t e to the t plus n e to the t, then my n plus 1th derivative is necessarily t e to the t plus n plus 1 e to the t. And since my proposition was true for n equals 1, it must be true for n equals 2, 3, 4, and so on. So that's proof by induction. You don't have to do this for your particular problem. However, if you can, it's more complete and correct. Well, coming back to our problem now, we are ready to put in an expression for the n plus 1th derivative. Our remainder is less than or equal to the max over t of e to the t plus n plus 1, sorry, t e to the t plus n plus 1 e to the t over n plus 1 factorial times x to the n for, excuse me, x to the n plus 1 for any value of x. Okay, where from here? Now, the first thing is that our t's are taken from 0 to x, and so it's pretty clear that x e to the x is an increasing function, and my maximum is going to take place at x. So we're going to say that this is equal to x e to the x plus n plus 1 e to the x all over n plus 1 factorial times x to the n plus 1. And what we want to do now is to show that as n goes to infinity, this Rn drops out to 0 for any value of x. Let's split up our terms here and see how they shake out. Our first term is going to be distributing, is going to be x to the n plus 2 e to the x over n plus 1 factorial. And our second term is going to be n plus 1 times e to the x, x to the n plus 1 over n plus 1 factorial. And we remember that we established a result earlier that as n goes to infinity, any x to the n over n factorial will go to 0. And the reason for that is that x to the n over n factorial is equal to x times x over 2 times x over 3 all the way out to x over n. And at some point, n is larger than x, so that x over n is less than 1. And if I now let n go out to infinity, multiplying by less than 1 as you go out gives you something that vanishes. Well, it will be less than any epsilon for epsilon greater than 0. So with that in mind, let's see if we can leverage that result for each of our terms. For our first term here, notice that I have n plus 1 factorial in the bottom, so I'm going to think of everything in terms of n plus 1. As n goes to infinity, n plus 1 goes to infinity also. And I have x times x to the n plus 1. And I have e to the x as well. And keep in mind that these are constants, so that this factor here goes to 0 times a constant, and we have 0. For my next term, n plus 1 over n plus 1 factorial is going to cancel the factor of n plus 1, leaving me with n factorial left behind. And again, I have a constant e to the x, one constant factor of x, and I have x to the n over n factorial, which goes to 0. And so all of this goes to 0 for any value of x, which means that Tn of x goes to f of x for large enough n. Let's recapitulate. We needed two things. First, we needed a pattern for our nth derivative, and we got that pattern by taking the first few derivatives and looking for a pattern. If we felt the great need to prove the pattern, we did so, but it's not necessary at this level of the game. Then, secondly, having done that, we went back and substituted our n plus 1th derivative in, and we looked for opportunities to let n go to infinity. It got a little messy, but in the end, we relied on the fact that x to the n over n factorial goes to 0,